2019, we're covering section 3.6, zeros of polynomials. Now, there are quite a few theorems in here and a little bit of manipulation to use, so I'll probably cut this section into two parts, okay? So let's get started with part one, the remainder theorem. What this says is that if we have a polynomial, p of x, and it's divided by a polynomial of the form x minus c, in other words, that x has a 1 coefficient and a 1 exponent, then the remainder is the value we get when we plug in c into the function. For example, let's skip the factor theorem for a second. Let's go down to example 1. Use the remainder theorem to determine the remainder of that rational expression. Well, we are dividing by the form x minus some number c, and it could be a negative or positive. But in this case, that just means that my c is 2, and this top numerator is my polynomial that I'm dividing. So let's plug in 2 into that top polynomial. We will get 2 times 2 cubed plus 42 minus 4 times 2. And if you simplify all of that, we would get 50. That means if we were to divide that binomial x minus 2 into the top polynomial, we would get a remainder of 50. Now it says we can use synthetic or long division to confirm our answer. Let me remind you of both, okay? So down here below, we are going to use synthetic. Synthetic only works when your denominator is of that binomial form, just a single x plus or minus a number. So we take our c value of 2. Our polynomial there isn't in descending powers. So I'm going to write it in descending powers above. I would start with my 2x cubed. Notice there is not an x squared, so we would put 0x squared. And then the next one would be my x terms, my negative 4x. And then my constant goes last, the plus 42. This is important because in synthetic, we only use the coefficients, but all of them in descending powers. So it's almost like a backwards division symbol here. And I'm going to write all of those coefficients here on the top, 2, 0, negative 4, and a positive 42. So here's what we do with synthetic. We bring down this first number, whatever it is, it's 2, and then we multiply by that outside number and bring it back up. And we do that every single time. So this becomes a 4. And then we add the 0 and 4 and get 4. We multiply it by this outside 2 again and get 8. We add the negative 4 and 8 and we get a positive 4. We multiply that outside 2 and the 4 and we get an 8, and we end up with 50 as our remainder. And for those of you who haven't been that familiar with synthetic, what those other numbers means, the 2, the 4, and the 4, is those are the coefficients of the polynomial that's remaining after we divide. So since we started with a 2x cubed, this means we're left with a 2x squared, 1 degree down, plus a 4x, plus a 4, and with a remainder of 50 over our divisor, which was x minus 2. So that's synthetic division. Now, although synthetic division, again, only works when we divide by a binomial of the form x, single x, plus or minus a number, long division works for everything. So let's review long division. Our divisor is x minus 2. And we're dividing into, but we still have to put it all in descending power. So we have 2x cubed plus a 0x squared minus a 4x plus of 42. And then our goal with long division is we want to multiply this x by something so we would get exactly a 2x cubed. Well, x times 2x squared would give us a 2x cubed. So I'm going to put a 2x squared in my squared column. And then I'm going to distribute. 2x squared times x is 2x cubed. 2x squared times my negative 2 is a negative 4x squared. But now we have to subtract. So I have a little thing that I say, change the sign, draw the line, then combine. That way we don't forget. So if we've done it right, our first two terms would add up to 0, which they do. So those are gone. Our next two terms give us a 4x squared. And then we keep going. So we can bring down our other guys, negative 4x and plus 42. And then we look at our first terms again. X times what will give us exactly a 4x squared. We're missing a 4x. So I'm going to write that here in my x column, a positive 4x. And when we distribute, you get 4x squared minus an 8x. But now we have to subtract. So we distribute that negative by changing the sign, drawing the line, and then combine. So again, we get a 0. So those guys are gone. We're left with a 4x here, and we go ahead and bring down the plus 42. Once again, we look at our leading terms. I want that x to look exactly like a 4x, so we're missing a 4. We put that 4 here in the constant column and distribute. 4 times the x gives us a 4x. 4 times negative 2 gives us a negative 8. And then we subtract by distributing a negative to the bottom. So we change the sign, draw the line, and when we combine, we get a remainder of 50 again. So 50 over x minus 2. So you can consider those either reviews of the synthetic division or long division, or, hey, I've never seen that before. There you go. Now you know synthetic and long division. So remember, long division always works, regardless of if it's an x or a 2x cubed that you're dividing by. Synthetic, it has to be in the form of a single x plus or minus a constant. Now, the one thing about having a remainder of anything other than 0 tells us that x minus 2 is not a factor of that top polynomial. Otherwise, it would have divided in evenly. So that's where our factor theorem comes in. So in the factor theorem, we're going to let p of x be a polynomial function, and then x minus c, this binomial, is a factor of p of x if and only if, remember our remainder theorem, if we were to plug in c into that function and we get a 0, that means no remainder. It divides evenly. And also, this term if and only if can be written as IFF in shorthand. You might see that later on in calculus as well. And it just means it works both ways. If x minus c is a factor of px, then we know the remainder is 0. Also, if we plug it in and we get a remainder of 0, then we know that it's a factor. Okay. So that's the part 1 and the part 2. It goes both ways. We just want to kind of recap here that if p of c equals 0, then c is a 0 of p of x. So we can also state the factor theorem as follows. C is a 0, which again is a root. We can think of it as an x-intercept, 0 root of the polynomial p of x, if and only if x minus c is a factor of p of x. All of these are telling us the same thing. Our y value is 0, therefore it lands on the x-axis, so it's an x-intercept or 0 or root. But also, if it's a 0, that means it is a factor. The x minus that value is a factor of the polynomial. It would divide in evenly. So let's move down here to the second example, where we're letting p of x equals the x cubed minus 7x plus 6. And we want to show that x minus 1 is a factor of p of x, and use this fact to factor it completely. If we know that this guy is a factor, that means the remainder, if we were to divide, would be 0. We can do the remainder theorem, p of 1. If I plug in 1, see if we get a 0. 1 cubed minus 7 times 1 plus 6 does in fact give us a 0. So by the factor theorem, x minus 1 is a factor of the polynomial p of x. Now it says it wants us to use that fact in order to factor it completely. That's where the division, either synthetic or long division, comes in handy, because then we can just kind of keep factoring those smaller pieces. So let's practice the synthetic only because it's faster. So here our 0 is x equals 1. So we're going to divide by that 1. And again, our original equation is x cubed in descending powers would be plus 0x squared minus 7x plus 6. Every type of term from the largest to the smallest has to be counted for. And then we put in those coefficients. 1, 0, -7, and 6. So we bring down the first one, multiply, combine, multiply, combine, multiply, and combine. So we do have a remainder of 0, and these are the coefficients of the other factor. So we get an x squared plus x minus 6. And again, how do we know it's an x squared? It's just 1 degree smaller than what we started with. If it's an x cubed, then that first coefficient belongs to an x squared. If we started with an x to the 5th, then that first coefficient would go to an x to the 4th, and it just decreases down. So now we have the x squared plus x minus 6, which we can factor. That factors into x plus 3 times x minus 2. And don't forget the first factor that they gave us. So p of x factors into x minus 1 times x plus 3 times x minus 2. So now we have the rational zeros theorem. So if this polynomial p of x has integer coefficients, and the first term can't be 0, and the last term can't be 0. In other words, there is a constant at the end. We'll make that note. Must have a constant. Then it's basically telling us every rational zero, remember a rational number means it could be written as a fraction. So every rational zero of that polynomial is of the form p over q, where p are the factors of your constant coefficient and q are factors of the leading coefficient. So let's sum this up. Possible rational zeros are going to be of the form where it's factors of the last constant, just a number by itself, divided by factors of the first coefficient. A couple of notes here. First of all, the rational zeros will be in the list, but that doesn't mean that all of those numbers are actual zeros. It just means they'll be chosen from that list. I don't know why that it is there. And we also want to make sure that we include both the positive and negative factors of that first and last constant. Let's do this example here. We want to find the rational zeros of this polynomial. 2x to the 4th minus 7x cubed plus 3x squared plus 8x minus 4. When we are finding rational zeros, we're only going to focus on the first and the last numbers. So let's first look at factors of -4. Okay. And remember, when we say factors, it would be integers or numbers that multiply to give us 4. Well, 1 is a factor of 4, so we've got plus or minus 1. 2 divides evenly into 4, and 4 divides evenly into 4. No other numbers divide evenly into 4. Now we want the factors of the first number. So factors of 2, not as many, plus or minus 1 and plus or minus 2. If we're looking for possible rational zeros, we're actually going to put every number from the top there, factors of -4, over every number of the factors of 2. So for example, 1 is a factor of 4. So possible rational zeros could be 1 over 1, or plus or minus that 1 over the 2. So I got the 1 from factors of 4, and that denominator, 1 of 2, are your factors of 2. So we've used this guy. Now we're going to use this guy, factors of 4. So we can have plus or minus 2 over 1, or plus or minus 2 over 2. And now we use the 4. We can have plus or minus 4 over 1, or plus or minus 4 over 2. Now, some of these repeat. So let's clean it up a little bit. Possible rational zeros. Plus or minus 1 over 1 is just plus or minus 1. And the next one is plus or minus 1/2. The next one is plus or minus 2. This guy here is just plus or minus 1, which we already have. So we go to the next one, plus or minus 4. And this last one reduces to plus or minus 2, which we already have. So now we're just looking at 4 numbers and their opposites. So we can use the factor theorem, plug these numbers in to see if anything gives us 0. We can also use the intermediate value theorem. If we happen to pick 2 numbers and one's positive, one negative, then that means there's a 0 in between. It may be one of our rationals as well. So looking at our original equation, we've already got some negatives in there and some positives. So I would start with easy numbers like 1 and -1, see if anything works. So let's plug in P of 1. We get 2 times 1 to the 4th minus 7 times 1 cubed plus 3 times 1 squared plus 8 times 1 minus 4. If we combine all of that, we actually get the number 2. So that tells us that this is not a 0. Let's try -1. We get 2 times -1 to the 4th minus 7 times -1 cubed plus 3 times -1 squared plus 8 times -1 minus 4. That one does in fact give us a 0. So we know x equals -1 is one of our zeros. Now we can plug in each and every one of those numbers, plus or minus 1/2, plus or minus 2, plus or minus 4, see which of those gives us 0. We can also use our calculator to help with that, one by using the graph, but also by using the table. Let me show you how. So if you go to the y equals, let's type in the function that was given us. One of the things that we can do is to hit graph, and we can kind of see approximately where those zeros are. Now remember, what we were finding were only the rational zeros. If a 0 is irrational, it's not going to show up in that list that we made. But this helps us break it down. Another thing we can do, though, is see this word table above graph. If we hit second function table, we can actually put in values for x, and it will automatically give us the values of y. For example, when we plugged in 1, we got a 2, and that's how we knew it wasn't a 0. But when we plugged in a -1, enter, we got in a 0. Now, if for some reason your table's not letting you put in values, go up here, see where it says table set, hit second function window, and you want to be sure that the independent variable is set to ask. That way you can type it in. The dependent variable should stay at auto. So let's go back to the table. And let's try some of the other values that we were looking for. We were looking for a -1/2, so we can plug in a -0.5. That didn't give us 0. We had a positive 1/2. There's another 0, positive 1/2. We can plug in 2. 2 is our third 0. Now, one of the things that you might remember from our polynomials is that it can have at most n zeros. So far we have 3. 1, 2, 3 zeros. Let's see if there are any more. So let's try -2. Nope. 4. Nope. And -4. No. So we only have 3 zeros at -1, 1/2, and 2. And our graph confirms that here at -1, 1/2, and 2. So remember that gave us P of a positive 1/2 equals 0 and P of 2 equals 0. So our rational zeros are -1, 1/2, and 2. Stay tuned for part 2 of what section are we in? 3.6. Okay, I know it's long, so take a deep breath. See you soon.